Okay, am I on? Good. Cool. Okay. So first of all, I'd like to acknowledge that we're on the traditional and unceded territory of the Squamish, Musqueam, and Tsleil-Waututh First Nations. And I'm here to talk about back pressure. So hopefully everybody knew what the topic of the talk is. My name's Sam Roberts. I'm a software developer at IBM Canada. I've been working with Node for about 4.5 years now, which doesn't seem that long in some ways, but Node's not that old. Oops. So what's back pressure? I didn't look up the Wikipedia definition. I would describe it as the ability of a receiver to slow a sender down to avoid getting overwhelmed by data. This is important because you can't control how many clients you have, how much are going to hit your endpoints. And so the problem is, if you can't control how much work is going to get thrown at your servers, and all of the work arrives, the reasonable thing to do is to buffer up the work. You get more requests than you can deal with right away. Maybe you have a big pipe. You either have lots of data coming to you, or you have lots of clients because your product is wildly successful, which is normally a good thing. But you have a slower back end. You're not able to make requests to your back end services or your databases as quickly as the requests are coming in from the client. If this happens in a spike, it's no problem to buffer up your requests. And then as you have capacity, you service requests, you respond, and you'll get over the spike. But if you have a continuous request rate that's faster than you're capable of responding to those requests, and the server is just collecting the requests, waiting till it can service them, eventually you're going to run out of memory. Now, the exact symptoms of this depends on your particular application, whether you literally run out of memories or you exhaust all socket descriptors, or however it is that your app is going to explode. It's going to get bigger and bigger and bigger, and it's going to pop like a balloon. And when it does, all of your clients, like not just the clients or the few clients that are perhaps overwhelming you, but everyone is going to die. Now, your servers will hopefully restart. You should be running under some sort of decent production system. But you don't want to have your servers die, taking down all of their clients and then have to restart them, even if Node is fast at restarting. So how do you deal with this? I mean, ultimately, we have a situation where there's more work that your clients want done than you're capable of dealing with. And there is no magic solution to that. You can't magically be doing more work. You can scale out, and you can respond, and hopefully your ops people are watching what's going on. But so given that you can't actually satisfy the requests, what are your options? Well, the options are to force the clients to buffer the requests. You don't want your servers to be using memory without bounds. So you want to push back to the work and not accept it unless you're ready to actually fulfill the request, actually do the work to make it happen. The underlying mechanics that makes this at all possible with HTTP is the TCP sliding window protocol. It's called, and basically how TCP works, well, I forget basically how TCP works, is every time a data packet is sent to arrives, there's an acknowledgement that's returned. So, okay, I've gotten this much data. But every acknowledgement comes with an extra bit of information, and that information is how much more data the stack is willing to accept. So TCP stacks will have a fixed amount of buffer space where they're willing to accept data off the network, hold it in the TCP stack, ready to be read by the application. And I guess in theory that could be a dynamically adjustable thing, but it's not. It tends to be a fixed quantity. So as the data arrives, if no application is reading that data, it's going to accumulate in the buffer, and every time some more data arrives, more data will be in the buffer, and the data will be acknowledged, And with the acknowledgement will come, okay, we only have this much space left. So the peer can send you that much more data. And eventually it'll fill up, the window will close in TCP talk, and the peer is not allowed to send any more data. There's nothing available. So this is the foundation of back pressure. This is what allows one TCP stack to tell another, don't send me any more data. I can't handle it. Buffer it yourself. And that's what will happen is the peer's TCP stack will be forced to buffer all that data, which is great because all your millions of clients on botnets that are trying to attack you, now it's their problem. Or perhaps they're just nice applications where you're super popular and they're trying to slash dot you. If people even use that term anymore, I don't know how popular slash dot is. So that's the base mechanism, what exists at the very bottom. So if you look at that, so that deals with what happens when the TCP stack's buffers fill up. But they fill up until they're read by the application. So in order to kick this mechanism into gear, it's important that the application only read data when it's really ready to process it. And if you just read the Node API, the Stream API, look at the HTTP API, you'll see that there's an event called the data event. And you can do, with any stream, you can do on data, pass it a callback, you'll get fed data, which is wonderful. It allows you to put together code like this. This is a really cheesy movie fetcher. It returns a great movie, Totoro, but only one movie. So every time you attach an on data to the file read stream, and every time you get some buffer gets read off disk and arrives in Node, you write it out to the client. When you receive the end event, that means there's no more data to come from disk. So you write out or you end the HTTP response. And you also deal with errors. A lot of streams, well, maybe I shouldn't be so judgmental, but there's a number of streams tutorials around that do not deal with the error flow. And that's not okay. Production servers, robust servers, need to deal with error propagation. So if there's an error reading from disk, it's unlikely to happen. File systems are pretty robust, but the unlikely is going to happen to your production servers. So when we get an error from the file read, we need to destroy the HTTP response to indicate that it's not complete. So this looks fine. This code works perfectly well and could work for a long time. The problem is, if you can read this movie faster from your disk than you can write it to your client, then Node isn't going to throw away all of the buffers that you did response.write. It's going to do the right thing. It's going to store them in memory, and they're going to accumulate without upper bound other than the size of the movie file here. And if you have lots and lots of clients all requesting the movie at the same time, all of them on not very good Wi-Fi's and internet cafes, then you, the server, eventually could have thousands of copies of this movie stored in your memory. And there's a limit to how much memory processes can use. And when you exceed that limit, Node will crash if it fails to allocate memory. So this is anti-pattern code. You should never do this. This is not the right way to move data from one source to another. So what Node APIs exist to deal with back pressure? And there's these two mechanisms that work together that streams have. So the first one is that when you write to a stream, the write method returns a Boolean, true or false. True means that the stream is not full. There's a high watermark on streams, though technically it's completely up to the stream implementation to determine what it means by I cannot accept more data. But if you push more data into a stream than it can process, it will still accept it, it'll buffer it, but it'll start returning false to the write method. And false means, hey, I'm now buffering data. You're writing faster than I can deal with it. So if you'd like to slow down, you can. If not, we'll use a little bit more memory or a lot more memory. So that's the first mechanism. You know that that is the back pressure. Responding with false is the stream attempting to push back and say, slow down. So in this example, the thing to do is you can pause the file reading. Once the response stream says you should slow down writing, you can pause reading from file, wait for the drain event. So the drain event on the stream means it has more buffer space available. So at that point, you can start writing to the response again. So you resume the file stream, start writing, and everything starts moving again. And of course, you deal with the end event. Now this method doesn't deal with errors because it's effectively what's done by the pipe API for streams. So readable streams already have the method called pipe. It looks like the code I just gave you, and it does not deal with error propagation. That's your problem. So this example in front of you is actually correct Node code. It will deal with back pressure. It will pause the read stream, the file system stream, when we're not able to push that data out to the clients, and it will propagate errors. So this is correct code, and you should not write it, in my opinion, and in the opinion of many people who use streams. Even in heavy stream shops, I've talked to a few who in code review will reject any code that makes calls to the pipe method. So you should be using the pump module. Pump basically does what you just saw. It does a pipe, but it also propagates errors. And error propagation is a little tricky because different stream objects actually have different ways of destroying them. There isn't a standard way to destroy a writable stream at this moment in Node. So there's a couple PRs going on right now to add pump to the Node core API, the Code Streams API. You can see the PR reference there if you want to read it. And there's also a related PR that I should have looked into this more closely. I believe it's landed at this point, that adds a destroy method to the streams interface. So there's a uniform way to destroy streams. Now the pump module knows about a bunch of different types of streams, and it knows the difference between HTTP and network streams, and it'll do the right thing to destroy them. So you don't have to deal with this, and it will propagate errors. And you don't see I'll show you an example later, but it also accepts multiple streams as an argument. It's kind of a classic stream kind of anti-pattern. You can have stream.pipe.pipe.pipe, and you can stick it on one line and it looks fabulous. And if any one of those intermediate streams has an error, lost. So it's not so great. So this is the right way to do things. Let's talk about the other side. So here we were, with that last one, we were sending large amounts of data to our clients. Let's talk about getting data from our clients. So this is simple code. It's really fast to get all of the data out of an HTTP request. I set the encoding to UTF-8 because that will cause the stream to give me strings and not buffers. And strings can be concatenated with strings, whereas buffers can't. I have an onData call again. Every time I get a bit of data, I append it to the string. When the request ends, I just JSON parse the data, which is pretty cheesy, but this is a small example. And then I end the response. So how many people have written code like this, actually? I mean, I totally have written code like this. Lots of us, right? As you're throwing out a couple lines of code in the middle of a unit test or whatever. Who cares what you do? But this, eventually, you do this in production, it's going to bite you. And if it doesn't bite you, then a hacker is going to find your endpoints, and then it is going to really bite you. Because there's no limit to how much data somebody can send you. With HTTP, you can literally send an infinite amount of data. You can just start sending data over a request. You don't have to say that it's over, and you can just start sending it. And I wrote a client that, in fact, does that to destroy my code here. So luckily, the first thing, luckily or unlucky, depending how you look at it, V8 has a maximum string size. It's about 256 megs. I found some docs that claims it's like 256 megs minus 32 bytes or something, though I was seeing slightly different numbers for some reason. But anyhow, it's about 256 megs. It's a maximum size of a string. With V8 which should land before 8.x goes LTS at the end of the month, it what is it, 1,024 megabytes. But the point is, it's still a fixed size. You go bigger than that, and string concatenation throws an error. And I don't know about you, but I don't normally wrap my plus equals with try catch and then kind of deal with it appropriately, right? So an Express server will catch the error and it'll do some right things. But the point is, this is not a good way to do things. Eventually, you're going to accumulate stuff. And what's also interesting is it's incredibly inefficient. As your strings get larger, once you have a couple, a 20 megabyte string, another 1,500 byte Ethernet packet comes in, it gets appended. So what does V8 do? It makes a new string. It mem copies all 20 megabytes of data over to the new string, adds 1,500 bytes at the end, throws away the old one. It's got a decent garbage collector, but why make garbage as fast as somebody can collect it? It doesn't make sense. So this isn't production code. You shouldn't actually do this. Interestingly, you can deal with the garbage collection problem by writing your code more efficiently. So don't convert things to strings. Accumulate all of your buffers on an array, and there's a buffer.concat call, which is nice. You can give it an array of buffers. It'll look through the buffers, see how much memory is needed to concatenate them, do one allocation, do one copy, and bingo. So this is a much better way, superficially, to accumulate your strings. But it still has the same problem. If the maximum size is over the 256 megabytes, it'll still explode. And what's even better is it took my laptop down. I had to hard restart it. Because it uses memory more efficiently, it's perfectly willing to accumulate that buffer array indefinitely. So if you're lucky, you'll hit the Linux out of memory killer and it'll take down your node process before your whole machine grinds to a crawl, which sometimes happened for me, and sometimes my machine just stopped because I just didn't have enough memory on my laptop. So this is also just not the way to do things. So the right way here actually is to use standard tools. If it's an Express application, there's a body parser, and the body parser knows how to parse JSON. Many people will use it just as a matter of course because it's less code. Why write any code to accumulate your requests if there's this nice body parser that does it for you? But one of the nice features of the body parser, something you might not even know about, is that it has a maximum size for the JSON. So when a bunch of clients either deliberately or accidentally or bugs happen, even clients have bugs, they will start sending you huge amounts of data. The body parser is going to start throwing things away after 100 kilobytes. It's like, no, it's too big. You can change the limit. It's configurable. You could lower it. You could raise it. But there is a limit. It's not going to eat all of your memory. There's another package called body, which is not so tied to Express. It's not designed as Express middleware. But it's still, it has the same thing. It also has a limit. I'm just checking the time here. Whatever. So if you use these tools, they're gonna do the right thing for you, and you're not gonna inadvertently get shot in the foot. So this is a different piece of code. So this is a code that basically it returns a table, selects star in a table, and returns it as CSV, comma separated values. So CSV files have it's a little bit of an ad hoc format, but usually the first line has some comma separated table titles, and then the rest of the data, every line is a row of data. So this looks like perfectly reasonable code. You select your user table. If there's an error, you deal with it. So actually, that is a terrible way of dealing with the error. Sorry, I can't believe I didn't. You probably should not be throwing your errors like that. You need to destroy the response and take down the query. But you're not going to do this at all because it's terrible code. So let's ignore the error handling for a second. But other than the error handling, this code kind of looks okay. You get back the result of the table. You format it as CSV. Use a nice map. Boom. Get a single string. Send the response. Life is good. But eventually, who knows how big the users table is? Right? In your test structure, you probably just have a few hundred users, or maybe two. Two is the minimal to have a test that actually tests multiplicity, right? So, But if eventually, maybe you're going to have millions of users, maybe you're going to be super successful, and maybe you're going to discover your production servers are not doing that well because they're reading these millions of records into memory, converting them all to a giant CSV file, it could be huge, and then trying to pump it out to the client. And once again, all of this data is going to be in your node process memory, sitting there, waiting for the client to receive it. It might go quickly, might not. I was describing, I was having a beer with a friend of mine, telling him I was giving this talk and kind of wondering, is this what would be or would not be useful? And he was like, he was kind of nice of him to say it, but he's like, that's a great talk. My team took down our production servers last week like that. Now, they had a slightly different example. For their example, they had a web client that was getting back JSON, and every row in the database table was getting converted to a JSON object, and they were concatenating all the JSON objects together. And again, he's got his big system, real production data. Some of those tables are huge for some of the clients. And it wasn't Node actually, but this problem exists in many languages. So the long and short is like, don't do this, or use the limit. I mean, if you really think your users table is never going to be more than 2,000 or 3,000 entries, or users is silly, but whatever if you never think, say you're returning the addresses or phone numbers associated with the user. I mean, how many phone numbers can a user have? Well, speaking as someone who used to do security work, as many as I can make, right? Well, if you have a nice API, some malicious person can just be like, how many million addresses can I add, right? And then how many million addresses can I query? So if you really think that your users should never have more than 20 addresses, or cell phone numbers, pick your number. Call it 100 if you want. Call it 1,000. But you probably shouldn't be allowing millions of cell phone numbers to be associated with your user, an individual user, and hoping that your production servers will stay up. So the way to deal with this, there's probably other ways, but the way I'm talking about here is to restructure your application object as a stream, because streams transmit back pressure. So in this case, we can do this with a transform stream. So transform streams are pretty easy to set up. The one little wrinkle here is that you need to use object mode. So what this means is streams, they have kind of two ways of working, one of which is they are a stream of bytes. Well, literally buffers actually, but buffers are chunks of bytes that are kind of moving through. But there's another mode for streams, which is object mode, wherein there's streams of JavaScript objects. And by objects, I mean, you could send functions through a stream if you felt like it. Typically, they're JavaScript objects. They're actually bits of, not literally JSON, but JavaScript objects that are used for their data values, their properties. So, and in this case, that's what you get from the SQL module, the MySQL module. If you do a select and you convert it to a stream, then what's going to come out of that stream is one JSON object per record. So we want to transform that into one CSV line per record. So we just create a transform object. We tell it that it needs to be using object mode, and we provide a single function that does the transformation. And that function will get called once for every object coming in, gets given a callback. When we have transformed the object, then we will call back with the output. In this case, the callback is all one line, but you can think of a transform object where perhaps I was going to look at the data, and then for one piece of the data, I was going to make yet another MySQL call. So your transform can be asynchronous. If it's going to take you a while, or you have to do some asynchronous work for every piece of data flowing through, that's okay, because the back pressure will apply as your transform streams accumulates unread work. So if the response is not reading everything from the transform stream as fast as it can, the transform stream will fill up and will tell tell the SQL stream, listen, stop getting me data. I can't deal with it. It's too fast. So the streams will magically do the back pressure for you. It's not really magic, but So there you go. The essence of the transform stream is set it to object mode, one function that takes your record, concatenate it with comma, sticks it to carriage return new line, and every CSV file starts with, well, not every, but ours always start with one line that describes the table names. So this is a back pressure respecting way to deal with this problem. And this code is okay, but you shouldn't actually write this code before checking npmjs.org. So this function exists already. CSV write stream. I think Max Ogden wrote it. He's got tons of streams modules. So it already exists. So this code is both respects back pressure, is short, easy to use. Well, this is the right way to do this kind of stuff. And we use pump. So this is an example of pump where multiple streams are being passed into pump. Now in that case, our transform stream didn't have any error events associated with it. But if there was times where the transforms could fail, it would be able to emit an error event that would be caught by the pump, and all three of those streams will be destroyed by the pump. Something that you would have to make sure that you wrote all the code for if you did that yourself. Let's see. So takeaways here is one, use standard tools. Standard tools should do the right thing under most conditions for your inputs, and so you don't have to think about it so much if they're doing the right thing. But when you're building your applications, or your API servers, or whatever you're building, it's worth, as you're building it, ask yourself, which parts of my API surface need to deal with large data, and which parts can just deal with limited data. I don't have to worry about huge amounts of memory pressure. So the ones you don't have to worry about, use standard tools. The ones that you do have to worry about, think about using streams to build back pressure aware systems for those parts. And for the parts that are not supposed to deal with large data, I would assert that they do not in fact use large data. Either stick a limit on every single SQL select statement to make sure that nothing ever happens unexpectedly, or do something. And it's not a good idea to make too strong an assumption about what your client's requests are like. And again, wily hackers and just unfortunate bugs are the reality of the world. And also, of course, you should be monitoring your servers. You want to know when your servers are exploding due to memory pressure. You want to know when they're restarting. The world is full of companies offering monitoring services and products. I work a bit on AppMetrics, IBM's monitoring thing. It's an open source plugin. You can add it to your applications, and it'll report memory usage and other interesting things about your servers. So at least if your servers do start dying regularly, you'll know. Nobody likes to get that pager call in the middle of the night, but it's better than being front page news on Slashdot, whatever. And okay, that's it. Apparently I talk faster in front of real people than in front of a mirror, so I think we're done all over there. Is there any questions? I can answer questions. Yes?
Yeah, so how does this relate to maybe any middleware that handles multi-part form data? So they basically tell you what my issue is there's a couple libraries. There's Multer, right? And then there's Express Busboy, right?
Okay.
These handle like our files, like multi-part form data.
Okay.
Do you know if any of these libraries implement these practices or don't?
Unfortunately, I can't. No, I don't know of any off the top of my head, but I can see the problem. Yeah, if your multi-part data, if it's all small, like most of the multi-part things, I think they will load everything into memory. You'll get your request, everything's parsed, which is great if each of the parts in the multi-part is not too big. And they'll probably, I would assume, would have limits on the size of all of the different parts. But if your parts can genuinely be huge, then you would want the parts to be you would want a streaming multi-part library. And I don't know if such thing exists. It'd be super fun to write one if it doesn't.
Okay, cool, yeah.
But
Basically, the question came up because our implementation was triggering an intrusion prevention system
okay.
on a VPN, and I didn't know if maybe some of the internals were Thank you.
Okay. There was one.
Yeah, so you said use standard libraries. Like, what do you consider standard libraries exactly?
Common tools. So this is a classic npmjs.org problem. There's a module for everything, and sometimes 25, and who knows which one is riddled with bugs and isn't, right? So that's difficult. I mean, their Express, I have a terrible memory, so I don't know off the top of my head, but the Express project is generating a library of middleware. So if it's released by the Express project, I would call it, fairly, they're careful people who take care of doing the right thing. In general, sorry?
Established packages.
Yeah, it can be difficult to know what's established. It is true. I mean, I have my own heuristics for looking at projects and being, okay, is this the kind of thing I'm going to have my apps depend on? I mean, I'll look at the GitHub repo. If they don't have a GitHub repo, it's not a deal breaker, but it's a bit of a red flag. Hopefully they have unit tests. If they don't, I mean, the code could still be right, but who knows? They hopefully they have some of their issue tracker. It's not a problem to have a huge number of issues in an issue tracker. I mean, nobody would ever use Node or NPM if they refused to use projects with large numbers of open issues. But you can kind of look at the type, and if nobody's responding to them, and it's it can be difficult. I'll also look at the code sometimes. Download stats are in npmjs.org as well. That helps, and you can also see if it's at 0.2. Maybe it's just the code was great, it does the job, and that's wonderful. But if it's a large enough code base and it's never been re-released in the last 3 years, you start to wonder about it. So, that's that. Do you have time for any more questions? No? We good? Really appreciate you. Thank you all for coming out.